Do you know what this is? It's the backbone of all of technology. Do you know how it works? Would you know how to put it into a circuit or build something around it? Well, by the end of this video, you will. So if you haven't figured it out yet, this is a transistor. A transistor can act as an amplifier or a switch. But to go from that basic knowledge to building an entire computer is a pretty big leap. But we're going to start you down that path. First, we're going to build a simple circuit. Then we're going to combine two circuits to build an oscillator. After that, we'll build a toggle circuit to turn the oscillator on and off. And then at the end, we're going to have more than just an abstract understanding of transistors. We're going to have a fairly complex system all built from scratch. For each of these circuits, I'm going to build on a breadboard, but I'm also going to show a schematic so you can see what's going on a little better. The parts we're going to need are 4 NPN transistors. We use the 2N2222. It's probably considered the most common and versatile transistor out there. We're going to use 10 1K resistors. We will only need one 10K resistor, 4 LEDs, 2 blue, 1 green, and 1 red, a 22 microfarad capacitor, a 1 microfarad capacitor, 2 tactile buttons, a piezo buzzer, a diode. For this project, you can use just about any diode, an optional thermistor, an optional photocell, some wires, and a breadboard. One of the easiest ways to power your projects are with a USB power supply, a little 5-volt power supply, and an old USB cable. I just cut the end off, strip the wires back, tin the wires, and you can plug those right into the breadboard. If you'd like to follow along with this and future projects, we offer a complete kit that has plenty of extra components in our store. All right, so let's get into this. We're going to start with the standard full-size breadboard. First thing I want to note is what's going on behind the scenes on a breadboard. You'll notice you have 2 power rails, one on each side. They run the entire length of the breadboard on these particular models. You have your positive and negative, but something to note is they are not connected. So this is a separate power rail than this. The other thing to notice is on the build section of the breadboard, which is between the power rails, there's 2 sections where the power rails are connected this way, the build section they're connected this way, and they are separated in the middle. So here's what it looks like inside of a breadboard. So you got the power rails, which go the entire length this way, and then you have your 2 build sections, which are split in the middle, and these are connected. So all these holes here are connected this way, and all these are connected this way, and then they're divided in the middle. Now that we understand how a breadboard works, let's jump into building a simple circuit. I think if we can break everything down to its least common denominator, it's going to help us digest the whole project. So on an LED, there are 3 primary ways to tell which is positive and negative. If the leads haven't been cut, the longer one is always the positive. If the leads have been cut, one thing you can do is look for the flat spot on one side. One side always has a flat spot. You might have to catch the light just right, but that is the negative. So the flat spot is on the negative. If for any reason you can't see that flat spot and you're still a little confused, you can look inside the LED and you can see there's a bigger portion and a smaller portion. The bigger portion is always the negative. Okay, so I already have this one cut down. And I have, you can see the negative is on the left. There's the flat spot. And we're going to put this in this way. And we're going to start wiring this up. So now we have the LED in there. We need to connect. I'm going to start with the ground, the negative. We have the negative to negative. And then I'm going to add the positive here. Now I'm going to hook it up and there we go. So we burned it out. I did that intentionally because I want you to know that you always have to run a resistor for an LED. We're not going to go into all the reasons why right now, but just know you always want to run a resistor with an LED. And since we're using a 5-volt power supply, I went ahead and chose a 1K resistor because that's more than enough to protect the LED. I'm going to take the one that we burn out. And here's the thing, it's kind of hard to tell. You can't really look in it and see that it's burnt out. You just have to test it and know. So I'm throwing that one away. And we're going to bring in a brand new LED, figure out which side's the negative. And here's the thing, it's not a big deal if you accidentally install it backwards. I'm going to intentionally install it backwards. So I ran it without a resistor, and now I'm running it with a resistor, but I'm running it backwards, and it just doesn't come on. So we can go ahead and turn that around, and you can see that now it's wired in properly. So that is a very basic circuit.
I know it's hard to see sometimes how things are connected on a breadboard, so I'm going to use a schematic here just to walk through the basics. I thought it'd be nice to use schematics because you can see what's going on a little more clearly. And we have some basic symbols here. You have your power supply, and it's usually labeled what voltage it is, and then this is the symbol for ground. You have the little squiggly line is your symbol for a resistor. And then the LED is typically a diode looking symbol, but with the circle around it and the little arrows, I guess, emanating light. So in this particular circuit, we have, and I'm going to show you in conventional current flow, which is from positive to negative. So you have your power coming from the positive. It goes through the resistor slowing down the current a little bit, so or limiting, I should say, the current so it doesn't burn out the LED. Goes through the LED, lights it up, and returns to ground. And that's the basic circuit right there.
Now, what I'm going to do is invert the circuit. So what I did is effectively shorted out the circuit, but it's not a true short because we have a 1K load here. So at 5 volts, a 1K resistor shorted across the leads is fine. It's not going to blow it out. But what it does is it gives the electricity a shorter path to follow because the wire has much less resistance than the LED. I showed you with a wire to make the point, but now I'm going to show you with a button. So now when you have a button there, you push the button, the light goes off. That's why it's an inverted circuit. So when I activate the signal, which is the button, it actually turns the light off. The reason I'm showing you all of this is because it helps demonstrate how a transistor works. On this particular transistor, you have a collector, which is the first leg over here. You have a base, and then you have an emitter. So what it's doing is, we'll pull the base out here separately. This is like a switch. When you activate the base by applying a voltage, you connect these two. What we're going to do is we're going to treat this very similarly to the switch that I just showed you. We're going to activate that center leg, which is going to connect the outer two. It'll create a short behind the LED, turning it off. Now the problem is I just did something very bad, and I wanted you to see that in this case we were okay, but sometimes you're going to end up blowing your transistor by doing that. Why? Because we didn't have a resistor. So resistors are our friends. It helps regulate and limit the flow of current because lots of current will harm things. We're going to add a resistor to the base, and when we power that base up, you'll see it activates the transistor, which is turning the LED off.
Okay, for the sake of clarity, I'm going to come back to the schematic here and talk through it. This is our wire lead here. It's coming from power through the resistor into the base of the transistor, which is activating it. But let's just assume that's disconnected for a moment, and let's follow the path. So if this is not active, this is like an open switch. It means there's no connection across here to here. So all of this is irrelevant if that's not connected. At least that's how we're going to look at it for this diagram. So what's happening is the power comes out, goes through the resistor, and it's going to follow the path of least resistance. And since this is an open circuit, it's going to go through the LED back to ground, and it lights up. And that is just your simple circuit right there. Now, once we activate the base, we are closing this connection here. So that's like almost like a solid wire going across there. So what happens is the electricity comes in, goes through the resistor. Now this has lower resistance than this, so it'll actually flow through that down here, robbing this of any energy and not lighting up that LED. So that's how this circuit is working.
Now that we've completed our inversion circuit, we're going to go to the second step, creating an oscillator. To start, we're going to have to duplicate this exact circuit that we created. Okay, so now we have our circuit duplicated. You can see when we add power, we've got two independent circuits right now. So let's just test them. We're gonna run power to the first one, turns off, second one, it turns off. Now here's where it starts to get a little bit interesting. Let's go ahead and connect them together and see what happens. Right now, what I'm gonna do is, I don't have to add these little jumpers, but I wanna make it a little visually cleaner. I'm gonna add these little yellow jumpers so we have a very clear input and output. Okay, so just to be clear here, we've got it set up so the input of the resistor is the input of this inversion circuit. The yellow is the output. So currently, because it's an inversion circuit, when the board is powered up, we have 5 volts coming out of this circuit. So in theory, if I take the output of the first one and run it to the input of the second one, what do you think will happen? Correct. It'll turn it out because this is powered. So it's sending 5 volts, and we just sent that 5 volts over to the other circuit, turning it out. So what do you think is going to happen if I power the first one now? When I power the first circuit, it turns the first light out. Since it is no longer sending 5 volts to the second circuit, the second light turns back on. Now that we know we can send power between the two circuits, we can create a loop. We already have the output of the first circuit connected to the input of the second circuit. So we just need to connect the output of the second circuit to the input of the first circuit. Time for the big reveal, and nothing is happening. Well, it looks like nothing is happening. That's because everything's happening instantaneously. If we want to make it interesting and we want to create this oscillator, we have to introduce a delay. To introduce a delay, we're going to use a resistor and a capacitor. We're not going to go into the details as to exactly how it all works. I'm going to show you that we want to take the output of the second one and run it to the input of the first one with a capacitor, and the wire is going to directly connect the output of the first one to the input of the second one. And then because a capacitor doesn't actually pass current, we need a little recharge here with a 10K resistor between the input and output of the first one. And this is going to create a little bit of a delay, and it gives us an oscillation.
Okay, I have the schematic here so we can see how everything's hooked up. We have 2 inversion circuits. Just if you want, I can segment these off. You got one here, so this is one inversion circuit, and then you have the other right here. And those are your 2 inversion circuits, and they're connected in parallel. The only 2 components we added a wire, from the out to the in, and then we added a capacitor from the in to the out over here, and then a resistor in between on this side between the in and an out, and that is to recharge that capacitor. So without going into all the gory details, that's the basic wiring diagram of this circuit.
So you can actually change the speed of the oscillation by changing the size of the capacitor. The smaller the value on the capacitor, the higher the frequency of the oscillation. So that's a visual oscillation. A lot of people may or may not know this, but an on-off or a high-low oscillation is really no different visually or audibly. It's an on-off. That means if we added a little speaker, we're going to put one end here, and I'm going to run that to ground. You should be able to hear what's going on. So that just sounds like a little bit of a click, but let me move this out of the way so I can get everything in there. Now I'm going to use a smaller value capacitor, and it looks like they're both on, but it's actually flickering so fast you can't see it. And what that's going to do is give us a higher frequency. So we're going to have a much faster oscillation, which equals a higher frequency, and you'll be able to hear it in the speaker. Oops, extra points if you notice my mistake. I connected the speaker wire to the positive leg of the power rail rather than the ground. In this case, it's okay. It'll work the same either way. The reason is because the signal going to the speaker is just an on-off signal, 5 volts to 0, or ground. And it's just pulsating between those two states. So technically you can go to positive or ground. It just needs a reference.
All right, up to this point, I've been giving you just enough information to be dangerous and have some fun. I'm going to go ahead and try to explain in a little more detail what's happening here. So this is our oscillating circuit where we have 2 inversion circuits. We have our little delay circuit up here, which is just the capacitor and the resistor, and then we added the speaker. So what's happening is, in concept, it's very simple concept, but it's a little harder to explain the flow of electrons. You have 2 inversion gates or 2 inversion circuits, and one turns on, and while it's on, the capacitor charges up. Once the capacitor is charged, then it activates the other one, which turns the first one off. So what's happening is you get this oscillation because there's 2 states to the capacitor, fully charged and fully discharged. And as it goes one way and the other, it turns on one and then the other. So again, without going into all the gory details of the electron flow, that's the basics of it. And these 2 allow that to happen. Now, what the speaker is doing is just piggybacking off of what's happening over here. So through this line, you're getting an oscillation of, positive, negative, positive, negative. And when I connected it up on the board, I actually connected it up wrong. I connected what was supposed to be on ground to the positive. Actually, I'm missing a little node here. I just realized that. The node should show you that it's connected to this and not this. So my apologies. But when I connected it to the positive, it still made a sound. It's because all this is doing is giving it a positive, negative pulsation. And then it going back and forth, it's making the speaker vibrate, and that's what gives you the sound. So whether you connect it to ground or positive, you're still going to get an oscillation.
Now that we have an oscillating circuit, we need a way to control it. We're going to do that with a toggle circuit, known as an SR latch. The really cool thing is the new circuit we're going to build is very similar to the circuit that we've already built. So to build our SR latch, we're going to need the same circuit, the inversion circuit. We're just going to duplicate both of these over here. Now we duplicated our 2 inversion circuits, we're going to connect them together. We're going to take a 1K resistor and go from the output of number 2 back to the input of number 1 of this circuit. And then we're going to take the output of number 1 and go to the input of number 2. And if we power it up at this point, you're going to see that one of them is active and the other is not. So let's just run power to the input of the first one. And you can see it switches to the second one. Now we're going to run power to the input of the second one, and it switches to the first one. That is a basic SR latch, but just to make it more official, we are going to add some little tactile buttons. Now you're going to see more wires added here, but don't get confused. We're just doing the same thing that I just showed you with the red wire. We're just going to make it work with a push button. The first button we are going to put to the first inversion circuit, and then the second button to the second inversion circuit. Set, reset, set, reset.
All right, I'm going to do my best to try to explain an SR latch and how it works very quickly. So what we're doing is we have the output of this one going through a resistor to the input of this one. And then the same thing going back the other direction from the output of this through a resistor to the input of this one. And these resistors are the same value, so it creates this hold state and nothing changes. So if this one's active, then it stays active. If this one's active, then it stays active. But they can't both be active at the same time. We added 2 push buttons, essentially to give one circuit or the other a little extra juice. And what that's doing is it throws that balance out of balance, and whichever one has more juice becomes the active one. I created a little visual display of what's happening here with some popsicle sticks and a marble. So what we're doing is, again, it's in a hold state because everything's in balance, but both can't be active. Just like just like this, you can't have both sides down at the same time. So what's happening is you push one button and it favors that side. Then you push the other button and it favors that side, but then it retains its hold state. But that's essentially how it's working.
Okay, now it's a little confusing because both lights are blue. We want to create an on-off switch. So let's disconnect our power. We're going to swap this one over here with a red light, and it's going to simulate our off position. And then we're going to swap this one with a green one. All right, let's power it back up. Now we have an easy way to visualize on and off. All right, I'm going to zoom out a little bit. And you can see we've completed 2 independent circuits. We have the SR latch we just created and the oscillator we completed in the step before. We can't hear the oscillator currently because I disconnected the ground wire. All right, I'm going to disconnect this so you can hear me. And the next piece that we're going to put in is called a diode. This diode allows electricity to move in one direction but not the other. The reason we want to use a diode is we want to be able to feed power from the SR latch over to the oscillator without it backfeeding back to the SR latch. These 2 circuits connect together from the output of the SR latch to the input of the first inverter on the oscillator. We're going to connect this back up so we got our sound. And now we're going to be able to turn our sound off. On, off. You might ask, why would you want to turn an annoying tone on and off? I'm glad you asked. What if we added a photocell? A photocell is essentially a resistor that allows current to flow whenever light hits it. If we add this photocell to the on position, you can see it comes on. I'm going to cover it up. And whenever the photocell is exposed to light, it activates the circuit. And you can't turn it off because it's still exposed to the light. So I have to cover it up and I can reset it. Now this one's kind of interesting. We have a thermistor. A thermistor is a resistor that is extra temperature sensitive. Okay, we're going to reset it, and here's what happens. Let's warm it up. And you see it activates it, and then you hit this to reset it. So what's really cool about a thermistor is you can adjust the temperature range, and now you've got a little warning device if something gets over a certain temperature. So with this one component, we were able to make a more complex system. We started with a transistor using it as a switch. We're able to build a little circuit around that, combine that into a bigger system, and eventually come out with a practical application. There's a lot you can do with this, and there's way more than I was able to cover in this video. I hope you were able to learn something, but more importantly, I hope you were inspired. I wanted to make this video because this is something that helped me get over a hump. I was able to learn so much more once I broke stuff down to its basic components like that. If you like this video and you want to follow along, we sell the kit in the store. It's got extra pieces parts, so if you burn out an LED or destroy a transistor, it's fine. There'll be extra pieces in there. Also,
in the description, we're going to have links to each one of these schematics, and we will also have all of the schematics that we ever make on our website, so you can always get them there.
I know everybody ends their videos the same way. I'm going to do it my way. I'm going to end with a joke. Why did the chicken cross the road? To hit the like button. All right, now subscribe. I'll see you next time.